Okay, so now that we've introduced the notion of dimension, and we've shown that any vector space has a well-defined dimension, which is either finite or infinite, we can use this dimension in practical ways. Now remember, dimension is the number of vectors in a linear independent spanning set. Okay, so one thing that we're going to want to, in other words, the number of vectors in the basis. So we're going to use these properties to create bases. So let's look at this first theorem called Goldilocks Theorem, which is kind of a strange name, but we'll see why that is in a minute. So let's suppose that we have a vector space and we want to find a linearly independent spanning set. Maybe we have a few vectors, but don't span W. So let's consider, for instance, suppose I'm in two-dimensional space. And this is two-dimensional space, and I have one vector. Now, of course, this one vector doesn't span the whole plane. It only spans this line. So let me throw in another vector that's not in the span of this line. And that turns out to span the whole, these two vectors will span the whole plane. Any vector here can be expressed as a linear combination of these two vectors through the parallelogram rule. All right, now these two vectors don't span the whole space. If I take another vector off the page and get three vectors, then those three vectors will span the space. Now notice each time I added a vector, I've added a vector that was not in the span that was already achieved. So that we're going to generalize that idea. So in order to get a larger linearly independent set, all I have to do is add another vector that's not in the span of the vectors that I have already. So let's see what the formal statement is. Suppose V is a vector space, and S is a linearly independent set of vectors from V. Now suppose W is a vector that's not in the span of this linearly independent set. Just like this example I gave here. I have two vectors that span the plane. Take another vector out of the plane. I can't draw it, but you can imagine taking a vector out of the plane, maybe straight out from the paper. So take another vector that's not in the span. Then this new set obtained by taking this new vector and adding it, this symbol means union, which means to add to this set. Add this new vector to the set of vectors I already have. This set will also be linearly independent. And the proof, well, how do you prove things are linearly independent? You want to see if they're not linearly dependent. Okay, so we're going to want to show that these set of vectors, V plus W, are linearly independent. We want to show they're not linearly dependent. Okay, so to show whether they're linearly dependent, we have to create a linear dependence relation. It's a homogeneous linear dependence relation. And there are two possible cases for a homogeneous linear dependence relation. One case is that AM plus 1 is equal to 0. One case is that the coefficient of W is equal to 0. In that case, what do we have? In that case, we have a linear dependence relation that doesn't involve this new vector W. But we already said that the vectors in V, the vectors in S are linearly independent. We already said that these vectors are linearly independent. So this cannot happen. Or it can only happen, that means that all the A's are equal to 0. There's no non-trivial linear dependence relation. On the other hand, so that's one possible case. It's possible that this coefficient of W is 0. Now suppose the coefficient is not 0. Then basically you can take this equation and solve for W, because you can divide by the coefficient. Okay? Now if this were true, we'd have W as a linear combination of the V's. But we already said that W is not in the span of S. Okay, so this case is also not possible. So what have we shown? We've shown that if we have linearly independent vectors and add another vector W that's not in the span, there cannot be a non-trivial linear dependence relation. So that means that these vectors, the vectors V, and include W also, must be linearly independent. Okay, so here's the Goldilocks theorem, and it's called Goldilocks, I guess, because it's either too small, too big, or just right. So let's go through this statement here. Suppose V is a vector space of dimension T. Let's have M vectors from V. Then you have four possibilities. Okay, so vector space has dimension T. This vector space is assumed to have dimension T. So there is a linear independent spanning set with t vectors. So let's just put that off to the side. I have W1 through Wt, which is a linearly independent set that spans V. Now suppose I take any set at all of vectors. And depending on M, I can draw conclusions. First of all, if M is bigger than T, then S is linearly dependent. Because we know that any number of vectors bigger than the dimension must be linearly dependent. If M is less than T, then S cannot span V. It's not a basis, so it can't span V. Okay. If M is equal to T and S is linearly independent, then S spans V, so it's another basis. If M is equal to T and S spans V, then S is linearly independent. So this is an if and only if. That if you have a vector space of dimension T and you have T linearly independent vectors, then it's a basis. On the other hand, if you have a vector space of dimension T and you have a linearly independent set that spans V, then it must have T vectors. And we've actually shown all of these things already, but we just go through the arguments again. If M is greater than T, then S is linearly dependent. We saw that before. That was this theorem, SSLD. Let me go back there. Okay, so this says that if you have a finite set of vectors which spans the vector space, that's your basis. If you have more than that, then they're linearly dependent. Okay. Okay. On the other hand, if you have fewer than T vectors and M does and you have a set that spans V, then you have one basis that has more vectors than another one. So that's also not possible. Okay, so let's go to this one. This one has something a little bit new. So look at this argument. Suppose that you have a set of T vectors that does not span V. Then you could choose another vector, and by the theorem we just proved, this set S, and throw in this additional vector, is still linearly independent. All right, so we'd have more than T vectors that are linearly independent, which is not possible. Okay, so this is the new wrinkle that if you have T linearly independent vectors and the basis of your vector space is T, then that set must form a basis. Okay. All right, now this last one is similar. Suppose I have T vectors that span V, and they're linearly dependent. Then you can go back to this proof, but basically you could solve for one of those vectors and remove that vector from the set, and it would still have the same span. Then we'd have a set of less than T vectors that had the same span as the T vectors, so we'd have two bases with different numbers of vectors, which is a contradiction. So what this is saying is that if you make a set too big, you put too many vectors, it's going to be linearly dependent. If you put too few vectors, it's not going to span. So the basis is just the right mix. It has enough vectors to span and not too many to be linearly dependent. Okay. All right, so let's look at some examples. All right, consider these two linearly independent sets of polynomials. And we've shown that these are linearly independent. Briefly, to show B is linearly independent, if you tried to make a linear dependence relation, well, you'd get A0 plus A1x plus A2x squared plus ANX to the n. The only way to make that polynomial 0 is if all of the coefficients are 0, so all of the a's are 0. On the other hand, for this set of polynomials, you can also show quite easily that it's linearly independent. If you had a linear dependence relation, well, the last polynomial is the only one that has x to the n, so that coefficient must be 0. Of the remaining polynomials, then the second to last polynomial is the only one that has x to the n minus 1, so that coefficient is 0. You could work your way down to the beginning. So these are both linearly independent sets. They both have n plus 1 vectors in them. We already know that this is a basis, so we could conclude immediately that this is also a basis. We wouldn't have to do any more work thanks to the theorem that we just showed. Okay, so here's another example. Suppose we have the subspace Z, and Z we showed already has a basis of two matrices. We could form two more matrices by taking linear combinations of these two. Those would also be in the same span, so they'd also be in Z. So here, taking 2 times the first plus minus 3 times the second, and then take 3 times the first plus 1 times the second, you get a new set of vectors. They're both in Z. You can show that they're linearly independent because in our usual way, form a linear dependence relation. This will give us 4 equations in the unknowns A1 and A2. And you solve this and you find out that the only solution is A1 equals A2 equals 0. So what does that tell us? That tells us that these two matrices are linearly independent. They're also in Z. And the dimension of Z is 2, so C is a basis. Okay, so we're good with that. Okay. Let's do one more example, sets of vectors in P4. Here we have 1, 2, 3, 4. Okay, we already showed this is a basis for the polynomials that have 2 as a root. Okay. Now, you can take these polynomials, 1, 2, 3. It turns out that 2 is a root of all of these polynomials, but this can't possibly be a basis because there aren't enough vectors in it. No. And here's another set of 1, 2, 3, 4, 5 vectors in W, and they're more than 4, and we know that dimension is 4, so these must be linearly dependent. Finally, we have this set of polynomials. These are all in W. There are 4 of them. You can check they're linearly independent, so automatically you know it's a basis. Okay, now, according to our intuitive idea of basis, if you have a smaller space, it should have a smaller dimension. Okay, now we do need to prove that formally, so let's go ahead and do that. Here's the formal statement of that idea. Suppose that U and V are subspaces of the vector space V, and U is contained in V but not equal to V. Then the dimension of U must be less than the dimension of V. Now, V could be all of the vector space W. This is just being proved in a general way. Okay, so in other words, you have W here, U is inside of that, U could be W, V is strictly smaller than U, and it turns out the dimension of V must be actually strictly smaller than the dimension of U. Okay, so suppose that the dimension of U is M and the dimension of V is T, then U has a basis B of size M because the dimension of U is M. Okay. And then, let's see, so B is linearly sorry, let me say that again. Suppose dimension of U is M and dimension of V is T. So M is this, so U is the, oh, I'm sorry, I did this wrong. This should be V on the outside and U on the inside. Sorry about that. V is on the outside, U is on the inside because U is smaller than V. Okay, so we suppose U has dimension M and V has dimension T. Okay, now it can't be, it's not possibly true that M is bigger than T because then you'd have a linearly independent set in U, which is also linearly independent in V, but the biggest the linear independent set can be in V is T. So it's not possible to have M bigger than T. Now if M is equal to T, then that means that this basis must also span V. So that means that U must be equal to V. So that's a contradiction. Okay. So the only possibility is that M is less than T. So smaller subspaces have smaller dimensions. Okay, so this theorem is related. Equal dimensions yields equal subspaces. Suppose that U and V are subspaces and that U is contained in V. Now you know actually that this contained could be equal to. And suppose the dimensions are equal, then the two spaces are equal. Okay, so let's follow this proof. These are the suppositions. U and V are subspaces. U is contained in V, and the dimension of U is equal to the dimension of V. So those are all given. So imagine your vector space and two subspaces. Okay. Now we want to show that U is equal to V. So let's prove by contradiction. Suppose that U is not equal to V. All right, since U is contained in V, there must be a vector V that's in V and not in U, because U is the smaller set. Now if U is not equal to V, there must be something in V that's not in U. Like this picture here. There must be something in between U and V. Okay. All right, now, so let B be a basis for U. Then we know that since this set V is not in U, then we have a linearly independent set consisting of these T vectors U and this vector V. That gives us T plus 1 linearly independent vectors. But V has the same dimension as U. Okay, so there's too many linearly independent vectors in V. So that's not possible. Okay, so if U is a subspace of V and has the same dimension, you can't find a vector between U and V, because if you could show that V has a larger dimension than U. Okay, so that's a very handy theorem. Basically the basis determines the subspace, and the dimension determines the subspace. And if you've got a subspace that contains T vectors, and it has dimension T, then that's the only subspace there is of that fits that condition. All right, so let me stop here.